So we will now continue with our investigation of the fundamental theorem of calculus. So we want to now look at differentiation of an indefinite integral. So what is an indefinite integral? It's so f from ab to r integrable and we define f of x equals f of a plus integral from a to x f dm1. So this is called the indefinite integral, and we want to see if its derivative is going to be equal to f almost everywhere, at least like in the fundamental theorem of calculus. So we already know that f is uniformly continuous and of bounded variation. Okay, so this much we know. So now let us, before we proceed, we need the following technical propositions. So f ab to r integrable and integral a to x f dm1 equal to 0 for all x in AB. Then f equal to 0 almost everywhere in AB. Okay, so the indefinite integral a to x equal to 0 for every x in AB, then you have that f has to be 0. So proof. So we define E plus to be the set of all x in AB such that fx is greater or equal to 0 and E minus equal set of all x in AB such that fx is less than 0. So to show m1 of E plus equals m1 of E minus equal to 0, then we are through, because then f will be equal to 0 almost everywhere. Okay, so assume, so we will do it for m plus, the proof for m minus is similar. So assume m1 of E plus, all these sets are measurable, so there is no problem. So then there exists f closed, f contained in E plus such that m1 of f is also positive. In fact, you can show that its measure is as close to E plus as measure of E plus as possible, and everything is finite measure here, and therefore in particular we are using a very weak condition here, namely m1 of f is strictly positive. Now u is equal to ab minus f is open, of course. So then u can be written as the union of n equals 1 to infinity a n b n, a countable union of open intervals. So let us set fn equals f times chi of union k equals 1 to n ak bk. Then on u we have fn converges to f because as n tends to infinity, and mod fn is less than or equal to mod f integrable. Therefore, by the dominated convergence theorem, integral on u f dm1 equals sigma n equals 1 to infinity of integral over a n b n of f dm1, which is the integral of f chi union n equals 1 to n a n bn. So that is nothing but integral a n bn of f dm1 and summation over n equals 1 to infinity. Okay. So now m1 of f is strictly positive, and f is also strictly positive on f because this is contained in E plus, and therefore you have that the integral on f of m1 f dm1 has to be strictly positive. Otherwise because if the integral of a non-negative function is 0, then the function has to be 0 almost everywhere. Therefore you have that 0 equals integral ab, that is given. Now it doesn't matter if we put the endpoints as closed or open, because those are of measure 0 and they don't matter. So what is it really doesn't matter, and that is equal to integral over u f dm1. Let us say integral ab is same as integral over open ab, and then plus integral over f dm1. And this one is strictly positive, and therefore you have integral over u f dm1 cannot be equal to 0. But what is integral over f dm1? It is the sum of the various things. Therefore there exists n such that integral over a n bn f dm1 is not equal to 0. But what is this equal to? This is equal to integral a to bn f dm1 minus integral a to an f dm1, and that is given to be 0 by hypothesis. As I said, we have that's it. Okay. And that's therefore a contradiction, and consequently this implies that m1 of E plus equal to 0. Similarly, m1 of E minus is also equal to 0, implies f equal to 0 almost everywhere. So proposition f ab to R bounded and integrable. Capital Fx equals f of a, that's some constant, plus integral a to x f dm1 x in ab. As I am repeatedly saying, it doesn't matter what when I put open or close at either end in such intervals, because the integral over points are all 0. Okay, so then f is differentiable almost everywhere, that we do already know, and f prime of x equals f of x almost everywhere in AB. So proof. So f is uniformly continuous and bounded variation implies f differentiable almost everywhere. We know this already. Okay. Now let us assume mod f less than or equal to m. So if n is in n, define fn of x equals n times f plus 1 by n f of x plus 1 by n minus fx, and that by definition is just n times integral x to x plus 1 by n f dm1. If f of x plus 1 by n is f of a plus a to x plus 1 by n f dm1, and f of x, so you just subtract, so by definition of f. Then fn converges to f dash almost everywhere as n tends to infinity, that is by just definition, and you also have mod fn is less than or equal to m, because mod f is less than or equal to m, so if you integrate over this, this will be less than or equal to m times 1 by n into n, and therefore this is also, you have this thing. Hence again by the dominated convergence theorem, that integral a to, let a less than c less than b. So integral a to c f dash dm1 is the limit as n tends to infinity, integral a to c of fn dm1 by the dominated convergence theorem. Now that is equal to limit n tending to infinity integral n times integral a to c f of x plus 1 by n dm1 of x, I am writing because I am writing the variable, minus f of x dm1x. Now we will write this as limit n tending to infinity n times, recall that integral a to c f of x plus 1 by n is nothing but a plus 1 by n c plus 1 by n, we have done this exercise before, f dm1 minus integral a to c f dm1. And now if you take, cancel out which is the common part, this is equal to limit n tending to infinity n times integral c to c plus 1 by n f dm1 minus n times integral a to a plus 1 by n f dm1. Now f is uniformly continuous, so given epsilon positive, there exists a capital N in n such that for all n greater or equal to capital N and for all x in AB, we have mod f of x plus 1 by n minus fx is less than epsilon. So if n is greater or equal to n and x belongs to AB, I am putting open B because I am taking x plus 1 by n, so it has to be inside the interval. Okay, you have that mod n of integral x plus 1 by n f dm1 minus f of x this is equal to mod n times integral x to x plus 1 by n, and I can also write it as a Riemann integral because it is continuous and so on. So x to x plus 1 by n of ft minus f of x no because fx is a constant dt and this is less than epsilon, and therefore when you bring it out you get n gets cancelled, so this is less than epsilon. Okay, for all n bigger than equal. So if you now take the limit here, therefore you have integral a to c f dash dm1 is the limit, so we are just taking the limit, so that is equal to f of c minus f of a, and that's equal to integral f dm1 in a to c, again by definition. So you have integral a to c f dash minus f dm1 equal to 0 for all c, and this implies that f dash equal to f almost everywhere by the previous proposition. Okay, so that proves the theorem. So now we want to get rid of the fact, we said if it's a bounded and integrable function, so we want to say the same thing without the boundedness hypothesis. So proposition, theorem, f from ab to r integrable, so there is no boundedness assumption anymore. Capital F of x equals capital F of a plus integral a to x f dm1, indefinite integral. Then f is differentiable almost everywhere and f dash equal to f almost everywhere. So this is like the fundamental theorem of calculus. Okay, so we have this in AB. Okay, proof. So assume f is non-negative, okay, and define fn of x equals f of x if f of x is less than or equal to n, this trick we have done before, and equal to n if f of x is bigger than n. So we cut it off at the value n. So then fn is bounded, integrable, and fn increases to f. So f minus fn is non-negative. Now you define gn of x equals integral a to x f minus fn dm1. So this is a non-negative function, so gn is monotonic, increasing, and hence differentiable almost everywhere because it's a monotonic function. We don't worry about what about this. This is, if this were bounded, then we know by the previous proposition this is differentiable, but because this is non-negative, we already know this is differentiable because this is now a monotonic function, and derivative is non-negative. Okay, and Fn is bounded, this implies d by dx of integral a to x Fn dm1 equals Fn almost everywhere. Now I am going to write Fx equals Fa plus Gn of x. Gn of x is f minus Fn plus integral a to x Fn dm1. Then f dash x, which exists almost everywhere because absolutely continuous, uniformly continuous function, is Gn dash x plus Fn x almost everywhere, and Gn dash is greater than or equal to 0, so this is greater than or equal to 0 Fn x. Now n is arbitrary, so this implies that f dash x is greater than or equal to fx almost everywhere. So integral f dash dm1 a b is greater than or equal to integral f dm1 a b, and that's equal to fb minus fa definition of f. On the other hand, f is non-negative, so capital F is monotonic increasing, and therefore integral AB f dash dm1 is less than or equal to fb minus fa, because for the monotonic functions we know that this is true. So therefore you have f dash bigger than or equal to fb minus a, f dash less than or equal to fb minus fa. This implies integral AB f dash dm1 equals fb minus fa equals integral f dm1 ab, and f dash is greater than or equal to f, and this implies that f dash equal to f almost everywhere. So this proves it for non-negative functions. So in general you take f equals f plus minus f minus, and then f of x equals f of a plus integral a to x f plus dm1 minus integral a to x f minus dm1, and then you get f dash x equal to f plus x minus f minus x almost everywhere, that is equal to f of x almost everywhere. You can write, how do you do that? You can put this as f1 and this function as f2, so f equals f1 minus f2, and then each one involves a non-negative function, so f dash equals f1 dash minus f2 dash, and f1 is equal to f plus minus f minus almost everywhere by the first step. Okay, so this proves that. So we have concluded that if you have an integrable function and then you define the indefinite integral, then it's differentiable almost everywhere and the derivative is equal to f dash. Okay. So the next time we will see when a function which has to be definitely bounded variation and uniformly continuous. So we want to know if when such a function, if there are any, what's the necessary and sufficient condition for it to be written as an indefinite integral and obviously it's an indefinite integral of its own derivative almost infinite. Okay, so with that we will stop.